The narrative that the AI race is a software speed contest is false. The real story is a hardware utilization crisis, where billions in capital expenditure are being consumed by inefficient architectures rather than profitable products. While headlines focus on corporate failure, the engineering reality involves specific bottlenecks like memory bandwidth limits and compute density mismatches that make current GPU-heavy models unsustainable without fundamental architectural shifts. We are trying to run software designed for general-purpose hardware on clusters that lack the specialized efficiency required for mass-scale inference. When a new AI model drops, the question that matters for most teams is not the leaderboard score or which company launched it first. It is whether your stack can run it reliably at scale and what it costs in electricity to keep those models alive. Today, we connect these headlines about burning money to the physical engineering trade-offs behind the hype. The industry has entered a phase where spending on semiconductor infrastructure is accelerating faster than revenue generation can catch up, creating a segmented bubble of financial fragility within a genuine technological revolution. The primary driver of this burn rate is not just the cost of chips themselves, but how they are utilized in production environments. Current training architectures and inference pipelines suffer from poor utilization rates on massive GPU clusters. Unlike specialized ASICs or application-specific integrated circuits that optimize for specific tasks, general-purpose GPUs often sit underutilized or bottlenecked by memory bandwidth during high-volume inference. This turns expensive hardware into a cash sink rather than an asset. Think of it like trying to run a Formula One car on a dirt road. You have immense power and speed potential built into the engine, but the terrain cannot support the efficiency required for long-distance travel. In our context, we are using high-power GPUs designed for flexibility and training massive models, yet forcing them to handle repetitive inference tasks where they lack the specialized memory architecture needed for throughput. The result is that every query processed burns significantly more energy than necessary because the hardware is fighting its own design constraints rather than working in harmony with the workload. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This inefficiency creates a trap known as the competitive task-based model. Firms are locked into an arms race where even when leadership understands that over-automation erodes consumer demand and thus revenue, competitive pressure forces individual firms to automate faster just to survive against rivals who do the same. Study data shows participants were 3.39 times more likely to forgo a guaranteed reward in favor of risky automation strategies. This leads to a collective loss where both workers and firm owners suffer from reduced purchasing power as costs rise without proportional value creation. The human cost of this dynamic is visible in the labor market, particularly for junior developers who are facing a hollowed-out middle class in tech. The entry-level job market has collapsed not just due to automation itself, but because of this specific economic trap where firms automate tasks faster than the economy can reabsorb workers into new roles. Standard economic fixes like upskilling or universal basic income fail here because the issue is structural. Rational decisions by individual companies lead to irrational collective outcomes that displace human labor at a pace the market cannot adapt to quickly enough. For developers watching this, your coding choices regarding model size versus inference latency have direct economic consequences. Pushing massive models onto general-purpose GPU clusters increases operational burn rates and creates bottlenecks that delay product viability. You might be optimizing for accuracy on a benchmark dataset while ignoring how those extra parameters translate into memory bandwidth saturation during real-world usage. Understanding the trade-off between simpler specialized hardware like ASICs versus flexible but expensive GPUs is now a critical career skill for system design. The industry is shifting from building bigger models to get better results toward optimizing architecture for energy and cost efficiency. Engineers who can design systems that minimize memory bandwidth bottlenecks or leverage specialized inference chips will be more valuable than those focused solely on model accuracy metrics. This shift requires a new kind of engineering judgment, where you must consider the physical constraints of your deployment environment as rigorously as the algorithmic performance of your code. We are also hitting hard limits in energy infrastructure that software optimization alone cannot bypass. Data center electricity consumption is projected to double from 485 terawatt-hours in 2025, turning power availability into a binding constraint for scaling AI without prohibitive costs. This creates a physical hard stop on current growth trajectories, where no amount of code refinement can overcome the lack of available kilowatts. The hardware demands are hitting ceilings that force a reevaluation of what is technically and economically feasible in the near future. Studies involving over 1,300 participants in controlled behavioral settings show that earnings decreased by between 10.7% and 42.9% due to AI-influenced decisions when efficiency was not prioritized. This data underscores that blind automation without architectural foresight leads to measurable financial losses for organizations attempting to scale too quickly on inefficient hardware stacks. The gap between what is technically possible and what is economically sustainable has widened into a chasm that threatens the viability of many current business models in the sector. The takeaway here is clear. The AI race isn't about who builds the smartest model. It's a hardware utilization crisis, where massive GPU clusters burn cash due to poor inference architecture. As we move forward, engineers must audit their own systems for efficiency rather than just capability. We need to ask not only if our models work, but whether they can run on the available power and memory constraints without draining resources faster than revenue is generated. This perspective changes how you approach system design in an AI-first world. It moves the conversation from pure software engineering into hardware-aware system design, where every line of code has a physical cost associated with it. The companies that survive this transition will be those that recognize these limits early and pivot their architectures to match the reality of energy constraints rather than chasing theoretical performance gains on inefficient hardware platforms. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.